we'll move on to our next speaker, who is Julie Krask from North Inlet-Winyah Bay, keeping it in the same region.
Okay, yeah, thanks Denise for teeing up North Inlet for me. Hi everyone, thanks for sticking around to the end here. I'm looking forward to sharing some of our findings that are a product of the Wetlands and Water Level Initiative, specifically some cascading biogeochemical effects of sea level rise that have been revealed as part of our salt marsh monitoring program along Crab Creek. So just to start, I assume everyone is somewhat oriented already, but I'll just give you a little more geographical context. Our reserve is located in South Carolina, about 60 miles north of Charleston and 45 miles south of Myrtle Beach. And our reserve encompasses the North Inlet Estuary, which is a classic back barrier ocean-dominated system. It's a very small estuary, and it's pretty well known among the research community for its near pristine condition. That status is largely because the estuary is surrounded by an undeveloped forested watershed. And so our salt marsh monitoring program was implemented along the platform of Crab Creek, which is denoted out in the figure on the bottom right. And key thing to note about Crab Creek is that it's the landwardmost subbasin of North Inlet. So this is also sort of, we're doing salt marsh monitoring, but we're also sort of simultaneously conducting a boundary study. And so the aerial figure here shows the two main segments of our monitoring program. And I'd also like to point out that one of our swamp stations is located just past the creek mouth. And also at that swamp station, we have a NOAA tide gauge. The tide gauge in particular has enabled us to get very high resolution measurements of water level over the years. A little more context on our specific sites. So we set up our program in two main segments across the Crab Creek marsh platform. And the idea is that these two main segments basically serve as the end members along a chronosequence of marsh development. So segment A is downstream, located further or near the creek mouth, and it is geologically older. It spans a comparatively wide distance between the forest and the creek. And you can see this in the elevation profiles that I've depicted on the bottom left-hand corner. So the red transects are all transects from segment A, and the blue transects are located at segment B. And you can see that the transects at A are much wider, much longer, and there's a more gradual sloping in elevation over the course of, or over the distance of the marsh platform. And much of the distance, that the extra distance located at segment A is made up of a wide-ish mid-marsh zone, which contains abundant mixed vegetation communities and salt pans. And then moving about a kilometer upstream, segment B is located adjacent to the creek terminus, which is an area of active expansion. So here the platform is much more condensed. There's a little bit of a narrow high marsh zone at the top of the transects, but as you can see in the profile, elevation abruptly drops off and most of the platform is classified as low marsh. And so the key takeaway here for our system is that while these segments are still part of the same small system and occupy the same boundary along Crab Creek, we've observed that their relative ages translate to differences in plant distribution, sediment properties, and all kinds of biogeochemical processes. And as we're all aware, so a major question motivating the WHEEL initiative is how wetlands will respond to sea level rise. So here I just want to show the long-term trend in Charleston Harbor, which is about the same as we're experiencing here in North Inlet. So the long-term trend indicates that we're having an increase of about 3.5 millimeters per year. However, right around the time that we implemented the WHEEL initiative, mean sea level seemed to have taken a dramatic upswing, and since then has been rising at a rate closer to about 14.5 millimeters per year. So somewhat fortuitously, over that time period of rapid acceleration, we've been able to collect a really robust set of data sets on all sorts of key salt marsh metrics. And so, of course, vegetation dynamics, inundation time, and elevation are always the priority data sets. We've also been measuring a number of ancillary parameters that are just as important for understanding marsh processes in biogeochemistry. And so one of the ancillary parameters that we've measured over the years is pore water nutrient concentrations. And so monthly measurements of both ammonium and phosphate collected over the growing season from the period of 2009 to 2019 show very dramatic increases nearly across the board at our marsh segments. So the figures here show the full time series of ammonium concentrations at each individual permanent plot along our 6 transects across our 2 segments. And when there are anywhere that there is a linear fit in the plot, the individual plot graph, that means that the trend over the long term was significant. And so as you can see, there's clearly a little bit of patchiness as far as the spatial patterns go. And the variability, there's some variability in the magnitude of the trend of increase over time. And occasionally we even have a couple of decreases. But overall, there's a very consistent pattern of increasing nutrient concentrations, particularly down in the low marsh. And so one thing I really want to emphasize with this is the scale of these increases. So at the beginning of the time series back in 2009, pore water concentrations were already much higher than ambient creek water in North Inlet, which typically for ammonium can range from about 2 to 10 micromolar. But as you can see, over this time period, we've observed rates that are pushing up concentrations to 2, 3, 400 micromolar of ammonium. And this has amounted to a rate of increase in some areas as high as 27 micromolar per year, which is staggering. And so the patterns observed in the pore water nutrient concentrations were particularly interesting in the context of some other long-term analyses we were doing with our creek swamp data. So long-term analysis of our nutrient data sets at the nearby swamp site revealed that concentrations in the tidal creeks have started to tick up slowly over time over the last decade or so. And it really looks like the beginning of that ramp up started about the same time that we're starting to see the increases in the pore water data from the Sentinel sites. So it's common knowledge that salt marsh pore waters can serve as sources of nutrients to the larger estuary by way of a process called tidal pumping. And so in this process, hydraulic forcing from tidal cycling draws out marsh pore water, which seeps into the tidal creeks and brings along those extremely high concentrations of nutrients. And so considering how much the nutrient concentrations have gone up over the last decade, or I guess from 2009 to 2019, and then also that modeling based on a lot of local pore water and marsh data has indicated that the tidal pumping mechanism intensifies considerably with higher flooding amplitudes. So based on that, we're sort of inferring that the patterns that we see in the creeks must in some way probably be related to sea level rise driven changes to salt marsh biogeochemistry. And then this is further supported by the fact that we really haven't been able to find any clear evidence of new anthropogenic drivers or watershed changes or upstream changes in environmental conditions such as precipitation that would be able to, explain the eutrophication that we're starting to observe in the tidal creeks around North Inlet. And then just to wrap up, a lot of this is a little bit redundant with what other folks have already highlighted, but just sort of this case study is a really good exemplification of the utility of the wheel data, particularly because through this initiative, we were able to detect somewhat subtler changes in marsh processes, but that doesn't mean that they have that they're any lower in importance for broader scale ecosystem implications, especially when we're thinking about nutrient cycling and eutrophication. And so with this data set, we were able to identify the cascading impacts of sea level rise, specifically that really completely natural changes to salt marsh biogeochemistry are driving the eutrophication that we're observing, or so we think. And so it's not like mitigating a specific, direct anthropogenic source of nutrients such as local runoff will be sufficient to really prevent ecosystem degradation. So basically the point is just that sea level rise clearly has collateral damage by a lot of natural pathways. And so it heightens the urgency to focus on the broader scale climate forcings and processes to try to figure out how we can, continue to keep our marshes alive. And that's all.
Super impressive. Eric has been trying to convince us to do pore water along our wheel transects for a long time, Julie. We can't necessarily do every quadrat monthly like you guys do, but is there a subset if you had just sampled in the season in one season in a few places, would it have been enough to detect the pattern?
I think so. I mean, it depends on how much you're consolidating into marsh zonation, but I mean, we definitely have a very thorough and robust data set, but I think, especially with the ammonium data and the phosphorus data, the trends were so consistent across the board with some sort of wonky exceptions that I feel like it would be hard to miss, especially again at that scale. Like it's such a massive increase. So
Well, cool. That sort of power analysis might be useful for recommendations for the other reserves. If you have more questions for Julie, just put them in the chat.